In the earlier lecture series, we saw how a plasma can freeze in the magnetic field, and these magnetic field lines can get annihilated in the reconnecting region, and the magnetic energy lost is pumped on the particle, and that's how the charged particles are accelerated. In this lecture series, we will see yet another interesting acceleration process by this frozen magnetic field, which do not require the annihilation of those field lines. As the plasma flows, the instabilities and the external factors, all are going to make this plasma flow to be turbulent. Now, since a plasma is a turbulent, you don't expect the frozen field to be uniform. Rather, there are a lot of magnetic inhomogeneities which are embedded with the turbulent structures, and as these turbulent structures move along the plasma, they can scatter off the charged particle, and the charged particle can get accelerated. And this process by which the moving turbulent structures can accelerate the charged particle by collision was first proposed by Fermi in 1949, and henceforth this acceleration process is called as a Fermi acceleration. Well, before we go into the detail of this Fermi acceleration, it is interesting to see how this magnetic inhomogeneity can scatter off the charged particle. So in this lecture, we will see this process, how a magnetic inhomogeneity can scatter off the particle, which is commonly referred as magnetic mirror. To start with, let us consider an uniform magnetic field, and let there be a charged particle with a velocity v. The force acting on the charged particle due to this magnetic field is given by our Lorentz force, that is equal to F is equal to Q by C into V cross B. Now, if I resolve this velocity of the charged particle into two components, one component along the field line, which I call as a V parallel, and another component which is perpendicular to the field line, which I call it as a V perpendicular or V perp. So now, because of the cross product, the one which is going to face this force, the force due to magnetic field, is a perpendicular component, and that force will be Q V perp B by C. Now, this force is going to be perpendicular to the velocity V perp as well as the magnetic field. So that will be out of this white board, or either the inverse, depending upon the charge of the particle, which doesn't matter for us, because what we know is going to give a torque, and that torque is going to make the charged particle spin over the magnetic field line. So eventually your V perpendicular is going to be converted into a spiral motion, or rather a circular motion around the magnetic field line. Now, since the V perp is going to cause a circular motion around the field line, and the V parallel is going to give a drag, so eventually the charged particle is going to make a helical trajectory guided by the magnetic field line. Well, if you look at the projection of this motion, it's going to be a circular, and there will be so it's circular, so there is going to be a force which is going to act towards the center, and that is the centripetal force, and that force will be mv perp square, because that's the velocity of gyration, divided by r, where r is the radius of the circular orbit. So this force is nothing but the one provided by the magnetic field. So this has to be equal to mv perp square divided by 4, because this is the only force acting on the particle in the field. So then I can cancel this here. Oops, sorry, this is r, because centripetal force is equal to mv square by r. So, and then I can write my r equal to mv perp c divided by qv. So this is going to be the radius of gyration around which gyration that the electron or charged particle is going to spin around the magnetic field line. So let me note it down here. So your R equal to mv per c by qb. Now, so the charged particle is going to spin around the magnetic field line in a circular orbit, so it's going to have an angular frequency. And that angular frequency you can always find it by, because we know formula is simpler. V perp equal to R omega. So R cross omega, we are taking it anyway. It's not tangential, so it's okay. I think R cross omega. So now when we substitute R from here, oh, sorry, this is a capital R. Radius is, yeah. So now if you substitute the R here, so what you are going to get is V perp is equal to M V perp C omega divided by QB, and V perp cancels. So this is going to give your angular frequency at which the particle is going to gyrate around the field line is going to be QB divided by MC. So let me note this one also. So we have the angular frequency omega is equal to QB divided by MC. So this is angular frequency, so the frequency will be this divided by 2 pi. So yeah, fine. And now, so if you see it, so it's going, a charged particle is going to move in a circle in a magnetic field. So this charged particle is going to, it's a current, so it's going to develop a current which is moving along a circle, and this current is going to create a magnetic field. So then we can always find out what is the magnetic moment by this charged particle which is moving in a circle. And the magnetic moment, which I denote it as mu, is given by the current I and the area in which it is being covering. So that area will be A. So now let us find out what will be my I. I is nothing but Q by T or dQ by dt. So I know the charge is I equal to, the charge is Q by T. So now 1 by T I can always write as Q into frequency. So this is the frequency, this is angular frequency. These both are connected by 2 pi. So this is going to be Q square B divided by, or I will write one more step so that you can see Q into nu is equal to this divided by 2 pi QB divided by 2 pi MC. So therefore this will be equal to Q square B divided by 2 pi MC. Now the area is nothing but pi R square, and of course we know R. So that's going to be pi into R square is M square V perp square C square divided by Q square and B square. Therefore, my mu is going to be I into A. So this will be I is Q square B divided by 2 pi MC into pi M square V perp square C square divided by Q square B square. Well, so Q square cancels off, pi cancels, and M square and M cancels, C square and C cancels, B and B square cancels. So what is left over is the magnetic moment mu is equal to, what is that left over? M V perp square or MC. MC V perp square divided by 2 times, anything else left over? B. Yes. Fine. MC V perp square B. So this is an interesting quantity which will be important in our further on as we go on. So this magnetic moment mu equal to MC V perp square divided by 2B. So now I'm going to do a technique. This uniform field line, I am going to pinch the line at the one end. Meaning that what I'm going to do is I'm going to increase the magnetic field density at some point, but I'm doing it a very gradual. Along the length scale, it will be very gradual change of the field I'm going to do. Now if you see, if the environment is on a slowly changing environment, the action integral over a periodic coordinate will be constant. This is what we call as an adiabatic invariant. We don't have to go into detail of it. We can just, if anyone interested, you can read the Jackson or Landau-Lifshitz, any book you can read, you can find out. So what is important here is, so in a slowly varying environment, this action integral over on a periodic coordinate is going to be invariant. And if you actually see in this process, when the magnetic field, when you consider the magnetic field and the charge of particle in the magnetic field, what is that invariant quantity is going to be this magnetic moment. So this magnetic moment, as I slowly going to change the field, this magnetic moment is an adiabatic invariant quantity, and that has to be always constant. And this gives an idea. So as I pinch the field, and so that I'm going to make it as an more higher magnetic field density at some point, the quantity which is going to be constant is this mu. So I can always write mcv per square by 2b needs to be constant throughout the motion. So this is simple. So this gives me an idea. So therefore, from here I can always write my v per is proportional to root of b. So this is interesting. So now, as the particle moves along this higher density magnetic density region, this perpendicular velocity, the gyration at which it is going to move, that is going to increase. So it's going to move, gyrate much faster. So let us have another one also. So now V perp is proportional to magnetic field. So if I put here, so you can always see. So then when I plug this V perp is proportional to B, so this is proportional to square root of B. So R will be inversely proportional to the square root of B. That is, your R is proportional to 1 by square root of B. So there are two things going to happen. As the charge particle, as my V parallel is going to drag this particle along the higher magnetic field line, so my V perp is going to, the particle is going to gyrate much faster, as well as the radius of the gyration is going to shorten. So this is the way as the particle moves in. So now let us have another discussion. So we will note it down this. So V perp, so your V perp is proportional to B, and your R is proportional to 1 by square root of B. And this will be a constant. I'm going to write one more term. So this is a constant. So now, the total electron energy, the charge particle energy, as it moves, they have to be conserved. So that means the total energy, there are two components of velocity. So there's only kinetic energy, so that will be half m v parallel square plus half m v perpendicular square should be conserved. That should be constant throughout the motion. So this says my v parallel square plus v perpendicular square should be constant. And this is another thing. So that means as the electron or the charge particle is dragged into the higher field region, we saw the perpendicular velocity has to increase. Now the total velocity has to be a constant. So now, as the V perpendicular is going to increase, your V parallel has to decrease. That means, as the charged particle is going to gyrate into the higher density region, it will slow down. And after some point, the particle, the V parallel becomes 0. That is when your V per square is going to become equal to the magnitude of the actual velocity. So the V parallel has to become 0. The particle stops. And now it can't remain there because of the higher field region. So the potential is higher and lower here. So the particle has to come back. So this is how the charged particle is going to be reflected by the magnetic inhomogeneity. And this is called as your magnetic mirror. Well, actually, so let us have another careful look about this, the trajectory of the particle. So the velocity vector is V, and this is V perpendicular, and this is your V parallel. So now, so this V parallel depend upon what is the angle, the magnitude of V depend upon is a V cos theta. So as the theta becomes larger and larger, the V parallel is going to increase. So you can always find out as the quantity, as this V parallel is becoming, as I reduce this angle, V parallel becoming larger and larger, the V parallel has some velocity which can overcome this pinch of this field, and it can eventually punch through. So I can, or for a very simple way, you can easily find it is, suppose if there is only a V parallel. So there is nothing V parallel. So it won't face any, it won't feel any stopping by this magnetic inhomogeneity. It will simply pass through. So similarly, you can say as this V parallel component keep increasing, there will be always certain V parallel component beyond which this inhomogeneity cannot reflect back the particle, rather it allows the particle to pass through. So this is going to give us one of the important term which normally in the plasma physics they use is as a loss cone. So there will be a cone. So if the velocity vector falls within that cone, it can actually punch through. The particle won't be reflected back. So for the particle to be reflected back, they should be out of this cone, and this cone is called as your loss cone. So when this idea popped up of this magnetic mirror, everything, it was very interesting, and what it was interesting. So if somehow, if the particles are being reflected within this, I have somehow used it to confine my plasma, which is very essential for the nuclear fusion, the power by nuclear fusion. So then it had a lot of strategic interest. So it was the idea of the confinement of plasma was treated as one of an secret project, and many people tried. And of course, the nature has a nice way to fool the people, and all attempts were wrong. So they were not able to confine, and then now we are having many advanced methods to confine. So one of the simple methods is what they call is a magnetic bottle. So it's something like this. So what they thought is, so if I have a charged particle here, the charged particle can be continuously kept reflected from both the sides, and it can actually confine the charged particle within this magnetic bottle. But it was not always easier, because the plasma can have a collision. At some point, somewhere else, the collision changes the velocity vector. At some point, the collision will bring the velocity vector within the loss cone, and once it reaches the loss cone, the particle escape out of it. So that was a serious problem. So they are not able to confine by this magnetic bottle. Then a lot of modifications came and everything. And nowadays we have the present day, the way they confine is to use a toroidal magnetic field, and the particle is being tied up within the magnetic field, which is called as tokamak. Anyway, so I am not a plasma physicist, so I'm not well aware about it. But so this is the concept, the toroidal magnetic field, and they do it out. And anyway, we are not bothered about how this magnetic field is going to affect this plasma on the terrestrial, because we are looking more into space. Let us go into the universe and see how this how this magnetic inhomogeneity is going to create some interesting properties. Now, as I said in the initial part, so this magnetic inhomogeneity is going to be associated with the turbulent structures in the plasma, and as the turbulent structure moves into the plasma, this can act as a scattering mirrors. So the particle can get scattered off and eventually they can get accelerated. In the next lecture, we will see, so here in this lecture, we saw when the magnetic inhomogeneity is stationary and the particle is coming and the particle is being scattered off by the mirror. Let us see what happens if this inhomogeneity is also moving and the particle is also moving, how this energy transfer is going to happen between the mirror and the particle. We will see it in the next lecture. Thank you.